Hi, AP Stats. This is Mrs. Harding. This video goes along with lesson 11.2b, which you can find in your OneNote notebook. There's really only one learning target for this, and that's to apply a test of independence, a chi-square test of independence. So let's take a look at this opening scenario. If you remember from 11.2a, we had talked about the chi-squared test of homogeneity. Today we're going to do the chi-squared test for independence, and we're going to talk about how the two are different. So it says there, number one, in a study of heart disease in male federal employees, researchers classified 356 volunteer subjects according to two categorical variables, their socioeconomic status and their smoking habits. And then the results are given here in the table. You can see there are three different levels for socioeconomic status, and there's three different levels for smoking habits. One thing to take note about this, and this is going to help you distinguish when to do a test of homogeneity and when to do a test of independence, is that in this particular example, we have one population of people that are being surveyed on two different variables, as opposed to the test for homogeneity where we were looking at multiple populations and their responses to the categorical variable. This is just one population, and we're trying to decide if within that population there is an association between these two variables. So when it comes to creating this test, we need to write our null and alternate hypothesis. For a test of independence, the null hypothesis is always there is no association between the two categorical variables, or another way to say that is that the two variables are independent. So in here, in this example, the null hypothesis would be there's no association between socioeconomic status and smoking habits of male federal employees. And then the alternate is that there is an association between SES and smoking habits. So then moving to page 2, remember that we've done a lot with two-way tables in the first semester. We even looked at whether or not two variables were independent of each other. And if you can remember back that far, we did conditional probabilities within the two-way table, and we compared the conditional probabilities. So we're going to start out with that just to see if there's any evidence in the problem, even from the beginning, that there's some sort of association between these two. When you go to determine your conditional probabilities, it doesn't matter which variable you assume to be the explanatory and which to be the response. For this example, we're going to consider socioeconomic status as the explanatory and then smoking habits as the response. So we're going to look at the conditional probabilities for smoking habits within each SES category. And you can see that that's what's shown in this table. So within the high SES category, we have the breakdown. 24.2% are current smokers, 43.6% are former smokers, and so on. And you can see that in this table, there does appear to be some sort of an association. You can see that for current smokers, the proportion that are low socioeconomic status is higher than that for high SES. And you can see in there actually middle socioeconomic status has the smallest likelihood there of never being a smoker. So there is some evidence, just looking at the conditional probabilities, that there is an association between the two. And you'll see on the next page that with a segmented bar graph, you can also visually see that there's likely an association, or you might expect there to be an association between the two variables. You can see in there that the parts of the segmented bar graph are not approximately the same. So do the distributions appear to be different? They do appear to be different in the segmented bar graph. So there is some evidence here of an association between SES and smoking habits. So what we're going to do is we're going to actually perform this test of independence to assess whether this observed difference is statistically significant or if it could just be due to chance variation. Okay, so on the next page is just a huge summary of this test for independence. So first you need your null and alternate hypothesis. The null hypothesis, there is no association between the two variables. Another way to say that is that they are independent. The alternate hypothesis is either to say there is an association or to say that they are not independent. And then you remember how to determine the chi-squared test statistic from 11-2A, that formula is still the same. The chi-squared test statistic is the observed minus the expected value squared over the expected value, summed across all of the cells. We're also going to need our degrees of freedom, which is the same, number of rows minus 1 times number of columns minus 1. And then the p-value is the area to the right of our test statistic on the chi-squared distribution. We also need to check conditions. They're listed there at the bottom. Remember, counts is not something that you need to actually specify and write out in your conditions, but you do need to check the random condition. You also need to check that all expected counts are at least 5. And you need to comment on the independence of the values, remembering that if you're sampling without replacement, to check the 10% condition. Finding the expected counts for each cell is done the same as the test for homogeneity, row total times column total over table total. So what you're looking at there is the observed and the expected values for each cell in our data. Do we meet the expected count condition? We do. Everything in there is at least 5. Have we met the randomization condition? No, actually they were volunteers that voluntarily answered the survey, so that condition isn't really met. So then are they independent of each other? Without the random condition being met, possibly not. But we're going to move ahead with the test and we're going to calculate the chi-squared test statistic the same as always. The degrees of freedom in this case, row minus 1 times column minus 1, 2 times 2 is 4. Sorry about the wavy writing. I'm not sure why it printed into OneNote that way. But when you're writing out the formula for the chi-squared test statistic, remember you have to write out the first couple terms and then the last term. You have observed count, 51, minus expected, 68.75 squared over 68.75, plus then the next cell. But you can certainly go to your calculator to get that value. With degrees of freedom of 4, you end up with a p-value of 9.81 times 10 to the negative 4th. This p-value is far less than 0.05, so we're going to reject the null hypothesis. There is evidence of an association between SES and smoking habits. And when I say go to your calculator to find these, you're just doing the chi-squared test. So hit the stat button, go to test, and then select the chi-squared test. All right, on the next page, there's a problem asking you to determine if there's a connection between political position and binge drinking. Students in a large statistics class at a university in the Northeast were asked to describe their political position and whether they had engaged in binge drinking. 5 drinks in a setting for males, 4 for females. The data is given below. At this time, I want you to pause the video and I want you to try this test for independence. All right, so assuming all conditions have been met, we're doing a chi-squared test for independence. You should have found all of the expected values by doing row total times column total over table total. You can do the test in your calculator. The degrees of freedom is 8. The p-value then is 0.26. With that, your conclusion would be that you failed to reject the null hypothesis. There's little evidence to suggest an association between political position and binge drinking. So one of the tough pieces about section 11.2 is determining when to use a test for homogeneity and when to use a test for independence. And it doesn't really help that often the way the question is phrased, it leads you to think that the test is one when it's actually the other. So for example, it might say, are these values independent, when actually it's a test for homogeneity. So you don't necessarily want to look to the question that's asked to determine whether it's homogeneity or independence. What you want to look at is, do I have one population for which I'm collecting data on 2 categorical variables? That would be a test of independence. Or am I collecting information on 1 categorical variable for separate, randomly selected populations? That would be the test for homogeneity. So that's what you want to look at in determining which test you're actually going to apply. So if you look at number 3, are men and women equally likely to suffer lingering fears from watching scary movies? Researchers asked a sample of 117 college students to write narrative accounts for their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms they experienced as a child are still present when they are alone at night. The following is a breakdown of these results. All right, so when you're looking at this, before you decide which test it is, have I collected multiple pieces of information from one population, or have I collected the same information from more than one population? And what you should have determined that this is just one population. So this is a test for independence or association. You have one population of 117 students, and you've collected their gender and whether they still suffer from fright symptoms. So flipping to the next page, very quickly, we're going to talk about what computer output looks like for a chi-square test. What you can see there is if we're taking the previous example and looking at the Minitab output for it, each cell is represented. And within that cell, you're going to see 3 different values. You're going to see the observed count, which is the top number, the expected count, which is the second number, and then the third number is the chi-squared contribution. So that's what you would get from observed minus expected squared over expected, and it tells you how much it's contributing to that test statistic. And then at the bottom, it gives you the degrees of freedom and the p-value. So in this example, which cell contributes the most? Well, it's the one that's boxed there because it has the largest contribution to the test statistics. So the difference between the observed and the expected is the most significant for that gender and lingering fear. What conclusion would you draw if alpha is equal to 0.01? Take a look at the p-value. The p-value is listed there, 0.045. We would actually fail to reject. So fail to reject the null hypothesis and conclude there is no association between gender and lingering fears. Flip to the next page. So then the last comment on this test for independence is what to do if the large counts condition isn't met, or what could be a possibility if the large counts condition isn't met. Take a look at the example there. It has living arrangements and age. We've collected information on 2,984 people and collected those 2 pieces of information. So this is a test for association or independence because it's just one single population. So if we went through and tried to decide if living arrangements and age had some sort of association, we would need to figure out our expected counts. So in the next table in part B, it has all those expected counts figured out for you. And you'll notice that for 19 and 20, other living arrangements, both of those cells have an expected count less than 5. So technically, we are not to proceed with this, or the results will not be valid. But there is one little trick you can do. So on the next page is just Minitab output for that scenario. You end up with 0 there, saying there is evidence of an association between age and living arrangements. But one of the, I've scrolled too far. Hold on. Sorry about that. I thought I had Minitab for both examples, and I'm far too into this lesson to start from the beginning again. So anyway, one of the tricks that you can do is you can actually combine categories. So one thing that I can do, since 19 and 20 right here, both of these expected counts are less than 5, I can just combine those 2. So I can just put all of that data together and have a category that is 19 or 20. And so then this is the Minitab output for that. You can see for 19 or 20 now, my expected count here for the other is 8.32, 5.10 still for 21. But now it's we sort of worked around that condition of the expected counts being at least 5. And then at the bottom is the results of the test. The chi-square test statistic is 162. Degrees of freedom is 8. The p-value there says 0. That just means it's so small that it's essentially 0. So now is the expected count condition met? Yes. What should we conclude? We're going to reject the null hypothesis. There's evidence of an association between age and living arrangements. Sorry for that confusion there on the last page. As always, if you have questions, please let me or Mr. Bowman know. Have a great day.